Pessoal, boa tarde, tudo bem? Bom, meu nome é Lucas, eu faço parte do Comitê, né, de Relações Internacionais, na verdade do EIRC, do escritório, e hoje a gente tem a felicidade de trazer o professor Bruno Callier. O Bruno é um professor, ele é físico, né, então ele é da universidade, é um professor titular da Universidade de Chapolion, em Albi, na França. O Bruno está aqui no Brasil em uma missão, né, CAPES COFECUB, então ele está visitando o professor Maurício Caiuti, lá na USP de Ribeirão, e aí a gente conseguiu um tempinho, ele, né, teve a disponibilidade de vir aqui para apresentar para a gente hoje a palestra dele, que está relacionada então com nanopartículas, né, de prata e entre outros metais. Então, o pessoal que está assistindo, né, daqui a pouco vai ter o QR Code para a lista de presença. Outra coisa, se tiverem dúvida, né, durante a transmissão, escrevam no chat que depois a gente entra em contato, a gente explica tudo as dúvidas que tiverem por lá, tá bom? No final também a gente abre, né, para a plateia as dúvidas, a gente tenta solucionar, tá bem? Bom, então, merci, Bruno.
Okay. Thank you, Luca. Eu não falo português, so I will speak in English. It's easier for me, so sorry for my bad English, okay? I'm not English, but so the title is Dielectric Barrier Discharge for Nanomaterial Synthesis. And first, I will present some background. Now, okay. For Zoom, okay. I came from Albi. Albi is in the south of the France, and it's a small town near Toulouse. So it's very small, and inhabitants is only 50,000. And so the students are only 4,000. So first, I made my degrees in Toulouse. First, the master degrees about the diagnostic and modeling of a plasma display cell. After that, I made a postdoc in characterization of phosphor under plasma excitation. Then I go to a private company doing some SEOX deposition on polymer at atmospheric pressure for a small company, Danone. Maybe you know. So after that, I joined the DPHE team in Albi. So as I'm a professor, I have teaching and I have duty. So here is the duty over the time. Mostly, we have to teach 250 hours per year, mostly. And I'm also the head of the department and are now head of a graduation. And mostly my teaching is numerical methods, so Python, mostly, and some plasma physics and other stuff. So Albi and the DPHE laboratory, the aim of the laboratory is the development of new plasma sources applied to biological decontamination on chemical application. So it's a small team. We are 2 professors, 3 assistant professors, 2 engineers, and almost 5 PhD. So we are part of the big University of Toulouse, who are quite big as USP now. So first, I will speak about some historical point to get to the plasma part, because I'm not sure you all will be aware of what is a plasma. So first, I will speak about that and some plasma-liquid interaction and some silver nanoparticle results production. So first, back in time, at the beginning, Mr. Thales discovers that amber and magnet, amber is the stones, and lodestones have some properties of keeping static electricity. After that, Pierre de Maricourt, maybe it's a French, Pierre de Maricourt, described the compass in back on time. It's the beginning. And after that, William Gilbert treats the Earth as a giant magnet and say, oh, if we have a magnet and we break in two, there is two magnets. So it's the first who has to speak about the term electric. And Otto von Guericke, maybe it's a German one, play with a rotating globe of sulfur, and he made the discovery that some feather will be attracted due to the electric statical point of view. So it's the first idea who lead to the first electric machine with static electricity. So they are quite inventive, and they build some machine like this one to allow to turn the global the glass, and in the same time they made some vacuum. So it's here, it's quite a long time ago, and they shows that there is an intense purple glow that appears. So it was the first plasma, because plasma is just a gas who can pass electricity. After that, they play with kids, like this one. They turn the ball, put the kid with some rope, and there is some spark at the finger of the boy. So they study almost the conductor and the insulators, like this. So as you know, Benjamin Franklin has made some study about some lightning rod with ear, and followed by the work of Bergman, who told us that any body in equilibrium, there is a neutral fluid composed of equal amounts of negative and positive fluid. So it's the beginning of electron and ions. Electron and ions. So Alessandro Volta made the first battery, and with zinc and copper and some electrolyte. So to get some high voltage, we can put them in parallel and in series. So here, in this room, it's just one battery. It's in France at École Polytechnique. So for this Humphrey Davy, the first English chemist who really invented the electric light. So at the beginning of the 19th century. So he connects two wires to a battery here, like this, the battery, and puts some strip of charcoal here, carbon, and he produces light. So it's the beginning of plasma discharge lamp. Also, he puts some strip of platinum who gets bright and incandescence and produce some light also. So what is a plasma? It's just a gas which has been ionized. So we have put some energy inside. So mostly for our work, it's electrical energy. It was neutral, and the electronic density is equal to the ionic density. So it's a gas who can conduct electricity. So some said it's the fourth state of the matter, because solid, liquid, gas, and if you put more energy, it will become a plasma. So there is inside some charged particle, electron and ions, and some neutral particle, excite, atom, molecule, and radicals. So there is a lot of different plasma, a lot, because it's about 95% of the matter in the universe. So some fusion experiment to interstellar gas. But for us, it's not me. Huh? For us, we will be only in this part with gas discharge, with lower temperature. Lower means here it's 10 to 100 electron volts. 1 electron volts is about 10,000 degrees. So low temperature. So mostly, I will speak about some plasma like this, who can be touched. And they are very soft. But the electron temperature is very high. But the ion temperature is low. There is a difference between the ion and the electron temperature. So I will be in time, don't worry. First, I will speak about some plasma liquid interaction for the production of nanoparticles. I'm not a chemist, so I may say some mistakes. So sorry. But first plasma setup is from this year, even before the term plasma exists. So it's just some experiments with Cubink's experiment, where silver is dissolved at the anode plus in the liquid electrolytes and reduced at the plasma electrolyte interface. So it's the first part of creation of particles, long time ago. So it leads to a field called plasma liquid interaction with a lot of work, where you where a lot of guys try a lot of things, like this one in 1953. He tried to reproduce some amino acid under the positive primitive Earth condition. He put everything together, ignite the discharge, and say, oh, okay. It was able to produce some amino acid from primary component, like with just this simple experiment. So there is a lot of works and there is a lot of review. So if you are interested, there is two, like this one. And the first one says something very simple. The chemical reaction in nanomaterial synthesis from plasma liquid interaction are in fact fairly simple. Okay. Most of the reactions are based on the reduction of a metal or semiconductor ions by electron provided by the plasma species. So it's quite simple, except for the discharge gas part, because you can have a discharge between an electrode and an electrolytic surface, but you can have a plasma with direct discharge between two electrodes, or a plasma between an electrode and the surface. You can have plasma radio frequency or microwave. There is a lot of plasma, in fact. In fact, here in pink, it's the plasma. So like this one, there is two electrodes. The liquid is on the lower part of the plasma, and you can get some particles. Or you can put an electrode and a tube for the liquid. You can put two electrodes and the discharge going through the liquid. You can make some gas and put the discharge, or one electrode inside on the top of the liquid and another inside the liquid. You can put an electrode inside and on the top. Here you can do a flux of gas, do the discharge between the surface and the liquid, or two tubes. Or even if you can do the plasma inside the liquid. So you have here some bubbling, and you met the plasma here. Or you can bubble in the other way. Or you can put the bubbling solution here and the plasma outside. There is a lot of configuration possible. Which one can lead to different results? So it's very tiny police of character, because there is a lot of work to do, and there is a lot of plasma sources. Here is the nanoparticle produced, so silver, 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 gold, 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 and under different condition of precursor and different condition of plasma. So if you want to pick, Luca want to do up some copper, okay. There is a guy who made copper with copper wire with a DC discharge. So it's possible. And in fact, if we speak about the plasma, what happened? You have your discharge area, and you produce some ions, UV, and excite species. If we are in air condition, you will produce also secondary reactive species like OH, NO, NO2, etc., etc. And all the particles, due to the flux, are going inside the liquid. So there is a penetration diffusion with some reactive species inside the liquid, who will lead to the reduction or something else. The half time of this particle are very different. They will live inside the liquid for this one infinite time. So you will produce, and they will stay in the beaker. They will stay inside the liquid, and other will disappear quite rapidly, like ozone. So because of the reducing species in plasma over liquid, it can only penetrate of a certain depth of the bulk liquid due to the limit energy and lifetime. So mainly the reaction took place in the plasma liquid interface. And you put some new species inside the liquid. So you change also the pH value. So you change also all your coefficient reaction, what you want. So as example, here I put, because I'm not a chemist, but I found some guy who makes some chemistry. Okay. Like the reduction of gold in acidic phase or in basic phase. So we can do both. No. Battery. Okay. So maybe. Okay. What we have done, I work with Professor Mauricio Caucci from USP at Ribeirão Preto, and we have a PhD sandwich, yeah, with France and Brazil, and his work was to make some silver nanoparticle by plasma, like this experiment. So it was in USP. So the experimental setup is quite simple. There is here a reactor, a glass reactor. We put some gas inside. Here it's helium gas. And we apply voltage between two electrodes. The plasma ignite here. And if we zoom, go through the surface. So we made some optical emission spectroscopy and some current measurement to characterize the plasma. We also make some optical emission spectroscopy from the nozzle to the surface. So we see here, for example, in black, it's OH. There is a decrease of the OH when you go away from the nozzle. But there is an increase of some ions and some nitrogen. So function of the distance you place your surface, you will not have the same species. So here, it's it's working. So here it's function of time. You see that here the plasma in the beaker. We produce some silver nanoparticles. The condition are with a capping agent as citrate and some experimental condition. Here we study the effect of the chemical parameters, so the citrate and the concentration of nitrate. So if we increase the citrate and the nitrate, we get some very big particle. So we made some absorption measurements to characterize the particles. So here it's at fixed concentration of silver and variable concentration of the citrates. So the peak is quite symmetric and very narrow, which is very good. But at high concentration of citrate, for example, 3 millimole, we increase the concentration of silver, and there is some shoulder who appears, leading us to think that there is two size particles inside, one bigger than the other. So if we want just one size, it's not the good solution. And of course, we made some microscopy to characterize the particles. And we saw that with high concentration, there is a lot of aggregation. So I'm here. Hopla. Click on the video, please. Here it's two videos. We made this solution yesterday because it's quite well known to produce particles, but we try to produce them directly in cellulose. So we can have some film with nanoparticle directly inside. So here it was gold and the other one was silver. We also made some application with the silver because it's a well-known decontamination agent. So here we have some Escherichia coli, so bacteria, and we put some solution of our silver nanoparticles. And we try to know if at a certain point they didn't survive. So it appeared at a certain time the bacteria didn't survive. And the other one, it's Staphylococcus aureus, who didn't survive also. So I was quick, but I can answer all of your questions. So we made an historical approach with a few mechanisms of plasma and plasma liquid interaction. I show you there is a lot of experimental setup in plasma. And I show you also that we can easily, in 5 minutes, synthesize some silver and gold particles alone or inside some film. So as a perspective, we need to better understand the mechanism of the plasma, which parameter will influence the size of the particles. Is it the voltage? Is it the distance? We also need to know the concentration of reactive species inside the plasma and the solution. So we need to develop some method to separating and quantify also the nanoparticles. And we made some biofilm. So as a for the end, it's a very multidisciplinary field, the plasma, because you have gas, so fluid mechanics, atomic and molecular physics, quantum mechanics, statistical physics, and radiative physics. Students love this. Yes, they love. And of course, with interaction with chemistry and some electrical engineering and some surface physics. So inter-laboratory collaboration are vital because I can't know everything. And if we work with Luca, he will know a better understanding of the chemistry, of course. So you can join me here. It's the old way, or here it's new way. Thank you. On time.
Thank you, Bruno. Pessoal, alguém tem alguma dúvida? Alguma questão? Comentar? Pode ser em português, a gente passa para ele depois. No? I have one question. When you produce silver nanoparticles, for example, when you produce, for example, by plasma, if you increase the plasma intensity, the nanoparticle, you increase the size of particles or the amount of particles?
We need to investigate because you first put more energy, so you will have quickly appear the particles, but we don't know if we will produce the same particle with the same amount of energy. So for the thesis of Tatiana, we fixed the parameter because with Mauricio, he made all the chemistry. So at fixed parameter, we study all the chemistry. But for the next one, we fix the chemistry and make the plasma vary.
We must add a reducer in solution, or just with plasma we can reduce this ion.
With the presence of reductor, it helps to be quicker. But normally you don't need it. Good question. It depends. Sometimes we use PVP or some other stabilizant. Of course. No, you understand everything? Almost. I was quick, but I see someone sleeping, so I try to wake up.
So thank you again, Bruno. Obrigado, pessoal, por ter comparecido. Obrigado.
Tchau, tchau.
Está para a lista de presentes. Obrigado mais uma vez.
On time.
Wow, on time.
Yeah.